Hello everyone, welcome to my civil engineering YouTube channel. Please subscribe to it and hit the bell icon to get notified when I post my new videos. Today I'll be discussing regarding first theorem of moment area. So it is also called as slope theorem, which is used to determine the slope of the deformed structure. So the second theorem of moment area, which is used to determine deflection of the deformed structural element. So coming on to the first concept of this lecture series, that is first theorem of the moment area method. I am just considering a simply supported beam here of span is equal to L here. So there are two supports you can just observe here. So there are two supports A and B which are simply supported in nature. So it is subjected to the simple concentrated load of magnitude equal to W here. So I just repeat it once again. So I am considering a simply supported beam of span is equal to L, which are of two simple supports A and B, and then is subjected to a point or a concentrated load of magnitude equal to W. So next figure, the figure B represents, the second figure represents here the deflected shape of the simply supported beam when it is subjected to the external load. And then I am just considering the point C and D here. You can just observe the 2 points C and D, which is in between the 2 points A and B, which is in between the 2 points A and B. So this C and D, between the length, between the points C and D, the distance, that distance is termed as dx. So the distance between the point C and D, it is an elementary length. So that distance is termed as dx, where dx is the elementary length between the points C and D, which is considered in between the points of supports A and B. In order to determine the slope for the elementary length, I have considered the 2 points C and D. So here, if I just, since the dx resembles an arc of a circle, okay, so dx resembles an arc of circle. If I just project that, dx, so that dx is the dx meet at a point O there. Okay, so that dx meets at a point O, wherein it makes an angle d theta. Can just observe here. So the dx is the elementary distance in between the points C and D. I am just considering that. So in order to determine this dx, it resembles in order to determine the slope here, so dx resembles a arc of the circle. So if I just project that arc, so it meets at the point O, you can just observe by making an angle of d theta. So let r be the radius of the arc. So r represents radius of the arc. Let theta CD, so let theta CD be the angle between the tangents drawn from the points C and D. So after considering the 2 points C and D in between the points A and B, I am going to project the tangents from the 2 points so that it meets at a single point where that it makes an angle. That angle is called as theta CD. Theta CD is an angle between the tangents drawn between the points C and D. So here again, delta is the deflected distance between the initial position to that of the final position. So here figure 3 represents the M by EI sketch sketch of overall beam, and the shaded portion here represents the points represents for the points C and D. So here it shows the M by EI sketch here. So M by EI diagram is nothing but the moment you are supposed to calculate the moment here. So M by EI diagram. So M by EI diagram, it represents here by a triangle here, since it is a concentrated load here, hence the M by EI diagram is in the form of triangular nature, and the shaded portion, it represents for the point between C and D. It represents for the point in between C and D. And then we are supposed to uh, validate the theorem here. So for that, we know that the bending moment equation. So as I said that from the Euler's Bernoulli's theory. So we have an equation that is M by I is equal to E by R. So M by I is equal to E by R. This is the bending stress equation, bending stress equation. So after that, I go back to the slide 2 here. So again I refer to the figure 2 here. So from the property of the circle here, I have that arc of the circle is equal to radius into angle. So from the arc property, from the circle property, I have arc of the circle is equal to product of radius into the angle to which it is made. Therefore I can write it straight away as for the portion only CD, I am going to calculate the slope. After that, I am going to integrate. So for the portion CD itself, I am going to consider the property of circle here first. So for that, the arc is equal to dx, that is equal to r d theta. So that is from the property of the circle, dx is equal to r times of d theta. Arc is dx, r times of d theta. This is the property of the circle here. So and then from this property of the circle, we have r is equal to dx by d theta. Substitute in this equation. So the value of r, so M by I is equal to E by dx by d theta. So what is d theta? So it is substitute that you just arrange that. So M by EI into dx. So this is the slope for the elementary length. So since the slope for the elementary length was d theta, therefore we have got the slope for the elementary length, that is for the points in between C and D. So for the CD portion, this is for the CD portion. So if I want for the overall if I want for the overall sketch, if I want for the overall diagram, so theta CD is the for the overall length. So theta CD, it is, you just consider here. So theta CD, it is for the overall what is that, overall beam, the slope for the overall beam, since it is through the point C, which is from A, right? So it is through point D, it is from B. Therefore theta CD can be considered for the overall structure. So theta CD is for overall structure. So theta will be equal to integration between C to D, integration in between C to D, M by EI times of dx. So integration C to D in integration limits will be C to D M by EI times of dx. Therefore the first moment theorem, the first theorem of moment area, it states that change in slope of a beam in between the 2 points is equal to area under curvature diagram between these 2 points. So I just repeat it once again. Change in slope of a beam between the 2 points is equal to area under curvature between those 2 points. So always you can just straight away take the theta value as I have said that theta value I am going to calculate for the portion between C and D. So in my first slide I have given the figure 3 here. So if I just calculate the area between this area of this project, the shaded portion, so straight away I can just find out what is the slope for the that amount of the area. So for the overall, it will be the area for the overall M by EI diagram in concern. So therefore, change in slope of a beam for between any 2 points is equal to area under curvature diagram between between those 2 points. So this is the validation for theorem 1. So coming on to the second theorem, so that is theorem 2, which is also called as deformation theorem, or it is used to find out the deflection. Again, I am just considering the simply supported beam AB of subjected to the load of W magnitude. Let C and D be the 2 points between the supports A and B. In order to determine the deflection for the elementary length, let delta be the deflection between the 2 points C and D, and let x be the distance from D to meet the point of tangent. Let theta CD be the angle between the tangents drawn from point C and D. I just repeat it once again. I am going to consider a simply supported beam of AB subjected to the load of W magnitude, and let C and D be the 2 points between the supports A and B. In order to determine the deflection the elementary length, let delta be the deflection between the points. Let delta be the deflection between the points CD, and x is a distance from D to the point where the tangent meets. So let theta CD be the angle between the tangents drawn from the points C and D. So again, I have the property of circles. So referring to the figure here, I can straight away take it as delta is equal to x into theta CD. I go back to the previous slide here. So delta is equal to x times of theta CD. So since this is also delta also will be in the form of arc itself, since always it is in the form of arc, so I can straight away take it as for the property of circle itself. So delta will be equal to x times of theta CD, what we have done for the previous theorem validation. So same way, delta is equal to x times of theta CD. So from the first moment area theorem, we know that theta CD is the integration value between M by EI into dx. Therefore, delta will be the theta CD into x. So substitute that, you will get what is the value of delta. So we need to substitute that and we'll get the value of delta. So deflection at a point in the beam. So here is a statement: deflection at a point in a beam in the direction perpendicular to its original straight line position, measured from the tangent to the elastic curve at another point, is given by moment of M by EI diagram about the point where the deflection has to be required. So this is in the simple words it can be explained as. So in the figure 1, in the slide 1, I have M by EI diagram here. So it is in the form of triangular format. So if I want to find out the moment somewhere at this point, deflection at this point, so that is nothing but deflection can be calculated as delta is equal to x into theta CD. We have proved that. So theta CD is nothing but the area. So area between the points, area between these 2 points I need to calculate. So area between the 2 points I will calculate. So after that, the centroidal distance, I mean the distance from any one of the support to that of the point, I'll calculate, and I'll multiply with that of the area, so that I will get what is the overall deflection at that point. So this is all about the deflection in concern. So the next point is that sign convention to be followed. So if I want to calculate the moments, so left hand side anti-clockwise moments are taken as positive, negative, and clockwise is taken as positive, and here in case of right hand side it is vice versa. So slope anti-clockwise angle are negative, so clockwise are taken as positive. If you remember any one, you can just you can remember the another also. So deflection right hand side tangent, if it is below the left hand side, right hand side tangent is below the left hand side tangent, then that deflection is taken as positive. So if the right hand side tangent is above the left hand side tangent, then it is taken as negative. So this is all about that. Thank you.